Yes, I hope slide is visible now. Hello.
Yes, sir.
Yes.
Yeah. So as I said, today we will discuss about the channel equalization. So do you have any idea about equalization? Have you studied anywhere?
Audio equalization. That's only no, sir. Equalization concept.
Concept of equalization. Studied anywhere in any of these subjects so far? Studied or not studied?
No, sir.
Not studied. Okay. You have studied about FIR filter, no?
Yes, sir.
Finite duration
Yeah.
impulse response filter, right? FIR filter.
Yes, sir.
Yeah, we use that filter, FIR filter, as a channel equalizer. Okay, so the purpose of this channel equalization is to remove the intersymbol interference. Okay, so you are all aware what is ISI, right? What is intersymbol interference? What it is actually? Anyone can say what do you mean by intersymbol interference? Yes, someone should respond. What you have understood? Why you can't define what is intersymbol interference? Yes, anyone can say no. At least say yes or no. You know how to define it, or you don't know how to define it. You can't define what is intersymbol interference after studying so much.
So interference between transmission of subsequent symbols.
See, what I said is if I transmit the digital information, 0 or 1 means sequence of zeros and ones, I represent 0 and 1 by a pulse, right? So what happens as it travels through the channel, the width of that pulse is going to spread. Okay, that is due to channel distortions. So at the receiver side, what happens when I started detecting the symbol, right? Means if I want to detect the say y of k is the, let me represent y of k is the received symbol at a time k, okay, which is equal to I can write h of 0 into x of k, okay, or just h into x of k, where h is the fading channel coefficient if I consider the channel is wireless, and x of k is the transmitted symbol at a time instant k. Okay, that plus noise will be there. So y of k is equal to, can think it is h into x of k plus I can represent v of k. See here, usually I represent noise as w, right? W of m, something w of n, like that. So any notation, right? So means what I mean to say is, let me just write with pen. So to say this is my y of k, okay. As I said, this y of k is the what? Received symbol at a time instant k. Okay. So which is equal to, I can write h into x of, this is x, okay, x of k, x of k plus vk, okay, plus v of k. So in this, what I said, this y of k is the what? Is the received symbol at a time instant k, and h I said is the, I will Oh, sorry. Okay, h into x of k it is okay. Okay, h into x of k plus v of k, right? So y of k is the received symbol at time instant k, and h is the fading channel coefficient. I said x of k is the transmitted symbol at time instant k, and this is the noise. Okay, so this is the model of the uh, wireless channel system without any intersymbol interference, because y of k is the what current received symbol, right? It depends only on the current transmitted symbol. So x of k is the current transmitted symbol along with the channel fading coefficient, right, plus noise. So here I say this is the model without any intersymbol interference. So let us consider another scenario where see y of k will be equal to h into x of k, or h of 0 and x of k, plus h of 1 into x of k minus 1 plus vk. Okay, if I consider another scenario, what I said, where y of k is equal to h of 0. Okay, shall I write, or is it you will be able to understand if I just say in words, because writing with this pen is not so much flexible. H of 0, okay, x of k uh, plus h of 1 into x of k minus 1 plus vk. Please write by yourself. I hope you are listening now. Hello.
Yes,
Yes.
sir.
Yes, sir.
Please write y of k is
Yes,
equal
sir.
to h of 0 into x of k plus h of 1 into x of k minus 1 plus v of k. Okay, in this case, what happens? The received symbol at time instant k depends not only on the present symbol x of k, it also depends on the previous symbol, that is x of k minus 1. Okay, we say in this case, second case, because of that x of k minus 1, we say there will be an interference, that is the intersymbol interference. Okay, I hope is it clear? In the first case, what I have considered here is without intersymbol interference, means the received symbol at time instant k depends only on the transmitted symbol at time instant k, means the current symbol, okay, depends on only the current transmitted symbol. But the second case, what I said, y of k is equal to h of 0 into x of k plus h of 1 into x of k minus 1 plus v of k, right? In this case, the received symbol at time instant k depends on the current symbol x of k and as well as the previous symbol x of k minus 1. I said that leads to intersymbol interference. Okay, so like that I have taken only for one. Right? It can be extended for n number of symbols, right? Means if I consider like that, I can write for n number of symbols. So if the received symbol at a time instant k depends on present and as well as previous symbols, that we call it as intersymbol interference, right? That leads to degradation in the performance of the communication system. Okay, so our goal is to eliminate that intersymbol interference. Means I need to eliminate here x of k minus 1. Okay, the received symbol y of k should depend only on the current symbol. It should not depend on the previous symbol. Means I need to eliminate x of k minus 1. So that is done by using this technique called channel equalization. I hope you have understood the importance of channel equalization. Okay, in one word to say, the purpose of channel equalization is to remove the effect of intersymbol interference. Okay, so where do we need to use this equalizer? We need to use the equalizer at the receiver side. Okay, after the receiving filter, if I use a equalizer, then I will be able to eliminate that intersymbol interference. Okay, so we classify these equalizers broadly as linear equalizer and non-linear equalizer. Okay, in that we discuss only the zero forcing equalizer, and another one is adaptive equalizer, where the coefficients, okay, will be varied according to the characteristics of the channel. Okay, for eliminating the intersymbol interference. That we call it as adaptive equalizer. And one more equalizer called a decision feedback equalizer, that will also be discussed in this module. Okay, so it is a very important concept and as well as topic in the communication system. I can give you the example of TDMA, right there, that is a time division multiple access. Okay, we'll be using this zero forcing equalizer. So it is a very important and interesting concept to understand. Please have a look properly, be focused to understand this concept. Okay. Okay. So let me take the first one. So as I said, sorry. See, the channels whose frequency response characteristics are either unknown, okay, or change with the time. Okay, usually we come across in practice this type of channels only. Okay, so change with time, or we will not be knowing the characteristics of that channel. Okay, well in advance. Okay, so that is one type of channel is known as a radio channel. Okay, so that is means it varies with time. Okay, so to say one example, see the data transmission over the dial-up telephone network. So this is a wide one. Okay, data transmission over the dial-up telephone network, where the communication channel will be different every time we dial the number, because the channel route will be different, right? So when we dial a number, so we keep dialing different numbers, right, for different. So it will take a different route. So because of that, the channel characteristics will be different, right? But after connection, once it connected, then the channel will become time invariant. Okay, fine. So this we say an example of channel whose characteristics are unknown before, unknown a priori. Okay. So another example where I said that time varying channel, right? So that is the example of radio channel. Radio channel means is a wireless channel. Okay. Even I can say example of ionospheric propagation channel. So means time usually we discuss as a linear time invariant, right? LTI system we discuss. Very rarely we discuss about linear time varying system, right? As time varies, the characteristics also will change. But in reality, the wireless channel is a time varying channel. Okay. So these channels are characterized by the time varying frequency response characteristics. Okay. So while designing the transmitting filter, okay, so we are supposed to use the square root raised cosine frequency response. So I discussed about the raised cosine role of filter, right? So that is one shape of the means pulse with which we will be able to achieve smooth uh, transition, right? It will means for different values of alpha, right? If you are remembered when I was discussing about the initial topics of this module, ISI, what is the criteria for zero ISI, Nyquist criteria, right? So there I discussed about that. So while designing, means we may design the transmitting filter that have square root raised cosine frequency response. So the transmitting filter frequency response is denoted by GT of f. Okay, GT of f, which is equal to square root of XRC of f. So this XRC of f means square root raised cosine frequency response it is. Okay, so into e power minus j 2 by f t naught. So t naught is the time delay. Okay, when the f is less than w. When f greater than w, it is 0. So this should be the frequency response of the transmitting filter. Right? Even C of f, I said that is the frequency response of the channel. Right? I used to assume it is a rectangular pulse, right? Which lies means its value will be equal to 1 between minus w to w. So similar to that, to study the time varying frequency response of the characteristics, I need to use a transmitting filter which has a square root raised cosine frequency response. So which is denoted by this formula. Okay, means this is the frequency response of the transmitting filter I say which is equal to square root of x RC of f into e power minus j 2 pi ft naught. Okay, and the receiving filter with frequency response gr of f. Okay, that should be matched to the what? Matched filter. That is GT of f, means transmitter filter and receiver filter frequency response should match, right? I hope if you have remembered, see GT of f into CR of this GR of f should be equal to X RC of f. Okay, because GT of f will be equal to GR of f, hence I can say GT of f equal to square root of X RC of f. Okay. So I think this one, right? GT of f into X GR of f is equal to X RC of f, right? I think this equation you are already familiar because when I transmit a sequence, okay, digital sequence or data sequence over the channel, due to channel distortion, right, the output of the receiving filter I get like this. Means at a time instant t, that is y of t is equal to, I can write an is the what? Magnitude of the sequence, either 1 or plus 1 or minus 1 depending upon the symbol, whether it is 0 or 1, and this is what? X of t minus nt, right? Fine, and this is the additive white Gaussian noise, right? So as I said, x of t will be equal to c, h of t is converted with gr of t. What is this gr of t? This is in time domain. What I have written this expression for output of the channel, that is output of the receiving filter in time domain it is. Okay. So x of t will be equal to what? H of t converted with gr of t. Gr of t is the what? This is the impulse response in time domain of the receiving filter. Right, h of t, which is equal to what? Gt of t converted with c of t. Right. So Gt of t is the what? Impulse response of the transmitting filter in time domain, and c of t is the impulse response of the channel in time domain. So what I mean to say is x of t is equal to h of t converted with gr of t. So which is equal to what? Gt of t converted with c of t, which is converted with gr of t. So this already I have discussed in the earlier lectures. I hope if you have studied, you will be able to recall and understand this, right? Because I said that GT of t is the impulse response of the transmitting filter, C of t is the impulse response of the channel, and GR of t is the impulse response of the receiving filter in the time domain. So that is equal to X of t. Okay. Even in discrete, I can write what is the filter output. Okay, at the receiver side, which is sampled periodically. Okay, so that is ym. This is in discrete form I am writing. So that is summation from n is equal to minus by infinity an x m minus n plus omega m or wm. Okay. So this is the additive noise, right? And as I said, when n is equal to m, okay, when n is equal to m, I can write it is as what? When n is equal to m, so it is x naught, n I am substituting as m. That is I am writing it is am, right? This is x naught am plus. So I can write for other values of this one. Means when n is not equal to m, I get this term. Okay, an x m minus n plus noise, right? So I said very well. This is the required symbol, right? At current one, and this one is what? This is due to the intersymbol interference, the middle term, and this is NO. I said it is due to additive white Gaussian noise. So this equation is also discussed earlier, right? So this is the output of the filter at the receiver side, uh, sampled at time t equal to nt, right? So that is xn is equal to x of nt, where I can vary the value of n as 0, plus or minus 1, plus or minus 2, and so on, right? So accordingly, I get the received symbol. Just in the beginning of this lecture also, I told what is y of k, right? So I taken time as variable k. Here, the time as variable as m. That's all. So don't be confused with these notations. But this is the present symbol, and these are the previous symbols, right? And it's the noise. So as I said, our aim is to eliminate this term, middle term, because this term is due to the contribution of intersymbol interference. Okay. Yeah. So in any practical system, okay, so it is reasonable to assume that the intersymbol interference will affect the finite number of symbols. Means instead of considering infinite number of sequence to say it will affect that one, so we consider some range of sequences over which it will affect the intersymbol interference. So here that is why we are assuming xn will be equal to 0, okay, for this value of n. I say n is less than minus L1 and when n is greater than L2. Okay, so where what is L1 and L2? These are the finite positive integers. Means usually in wireless communication, that too in 2G standard, the value of L1 and L2 varies between 2 to 5. Okay, the value of L1 is taken as 2 and L2 taken as 5. So the ISI, okay, observed at the output of the receiving filter may be viewed as being generated by passing the data sequence AM through an FIR filter. So that is why I am coming here to the finite duration impulse response filter. So what I am thinking here is I can think that ISI observed at the output of the receiving filter may be viewed as being generated by passing the data sequence AM. Okay, this is the data sequence, input data sequence, which I am passing through the FIR filter, with a finite duration impulse response filter, with the coefficients xn. Okay, the value of that xn varies from this to this, that is from minus L1 to L2. Okay, so that we call it as a equivalent discrete time channel filter. The moment I say FIR filter, what you all will visualize? Is it possible to say from your side, FIR filter, how the structure will be? Anyone can say, because you have studied in DSP, 5th semester. The structure of FIR filter.
Inverse Laplace transform and summers.
Inverse Laplace transform.
I mean, sorry, inverse Z transform. Sorry.
Inverse jet transform, that is what. Right. Means, see, there will be a sequence of delay elements we can write. Right, delay elements. So through that the data will be passed. Then there will be weights also, right, for each delay element. Then output of that will be multiplied and then it will be summed up. Okay, that will be the output of that filter. I think if I show this diagram, you'll be able to visualize, right? So this is my input data sequence AM. Okay, I'm assuming that ISI will be viewed as what output of this. Okay, this one. See, this is my input data sequence. That data sequence will be passing through these delay elements. So here the delay value will be the symbol duration T. Okay, and these are the what weighing functions, right? Right. So that is x minus L1, x minus L1 plus 1, then x minus 1, x naught. Similarly, this side, x L2 minus 1 up to x L2, right? So output of these will be added together, means summer, right? Output of that one will be the output of the FIR filter. Okay, finite duration impulse response filter. I can write that as, means if I denote this as y of k something, so which is equal to summation from k, that is from minus L1 to L2, right? That is the range from minus L1 to L2. So xk, right? Then am minus k. So this is the data sequence am, right? And this one is the what weighing function. I hope maybe the notations are different where you have discussed in DSP, right? But the thing is same concept. So this is a FIR filter only. So equalizing filter, right? So equivalent discrete time channel filter. I think, could you get this point? Only I said the notations are different. Maybe there you are writing as delay element. Okay, here the T I have written. Okay, this is a delay element, and this is a weighing factor for each this one. So output of all those things will be added together to get the output of that filter. Okay, summation that ranges from minus L1 to L2 xk am minus k. So how many of you could recall from your that DSP FIR filter design? Yes, I hope it is clear. So what I said, I am weaving. So this sentence in part, see, ISI observed that the output of the receiving filter may be viewed as what I am saying, being generated by passing the data sequence AM through an FIR filter with the coefficients what xn, where the value of n lies between minus L1 to L2, right? So I call that as a equivalent discrete time channel filter. Okay, that equivalent discrete time channel filter is this. I hope this point is clear, right? If we substitute the value of x naught, means when k is 0, right? K is 0, what I get? X naught AM. That is a present symbol, right? Then k is 1, 2, 3, and so on. Means you take any value of L2. So I said 5, no? And L1 is minus 2, just 2, right? So minus 2 to 5, if you substitute the values and vary, then you will understand, oh, present symbol depends on present received output symbol depends on present and as well as previous also. Okay, so it should depend only on the present, but when it is depending on previous symbols also, that leads to what I said, inter-symbol interference. So our goal is to eliminate that inter-symbol interference. How do we design a filter which can eliminate, which will eliminate those ISI? Okay, that is what we are going to discuss. So I'm just putting this problem in this form. Okay, I'm assuming the output ISI observed at the output of the receiving filter will be is what I am treating the data sequence is passing through the FIR filter, right, with coefficients varies from minus L1 to L2. The output of that will be this. Okay. So as I was telling about that input sequence, now it may be binary or it may be M-array also. Accordingly, the output of the discrete time channel filter may be characterized as the output of the finite state machine with the states what L is equal to L1 plus L2, right? And which is corrected by the additive Gaussian noise. Okay. The noise-free output of the filter will be described by the trellis having m power L states. Okay, L is what? This one, L1 plus L2. Okay, noise-free output of the filter is described by the trellis having the m power L states, where I said L is equal to L1 plus L2. So it is not very much about this because I'm not going to discuss again about this trellis diagram or even maximum likelihood sequence. Because that is also part of this. I'm skipping that at this moment of time. Okay, since there is no continuity with that maximum likelihood sequence. If you have studied, you have remembered, then I think it will be helpful. Otherwise, you can have a look from the textbook. Okay, so let me continue with this. So now let me say about the linear equalizer. So far what I've discussed is only about that y of k, means how it depends on present symbol and as well as the previous symbol. So I generalized that and I'm treating that as the data sequence is passed through an FIR filter. The output of the FIR filter is similar to the what I get the output of the receiver filter with ISI. That is what I wanted to convey. Okay. So now, as I said, these equalizers are used for what? Removing the effects of inter-symbol interference, right? Already I defined that. So what is equalizer or just channel equalizer? Equalizer and channel equalizer are same. Okay. So these filter parameters are adjusted on the basis of what? Measurements of the channel characteristics. So the channels whose frequency response characteristics are unknown and time variant. So I said the radio channel is a time variant, right? So we use the linear filters, okay, with adjustable parameters. Means I will be able to vary the tap, we call as tap. Okay, I will be able to vary the taps so that I can adjust and make it balance. Okay, means I have a mechanism to nullify the existence of the previous symbols at the output of the filter. Okay, then I can say output of the filter depends only on the present input symbol, not on the previous symbols. So where I have the mechanism such that I will be able to vary the parameters periodically. So such a filter is known as the adaptive equalizer. Okay, means depending upon the characteristics and parameters of the channel, I will be able to vary the parameters of the filter. So with that, I have a flexibility, right? So means adaptability will be there. Hence the name adaptive equalizer. Let us see what is that adaptability and how it works and all with it by taking one example. Okay, so before that, let me say about this zero forcing equalizer or just linear equalizer. Okay, so first we'll consider the design of this characteristics of the linear equalizer from the frequency domain viewpoint. Okay, then we'll have a time domain viewpoint. Then the picture will be clear. So we will discuss in both time domain and as well as frequency domain. So this is the block diagram of the PM transmission with the use of equalizer. See, the input data sequence, that is AM, is passed through the transmitting filter having a frequency response of what? GT of F. Then I have channel with its frequency response denoted as C of F, right? Then noise will be added in the channel. Then this is a receiving filter at the receiver side, right? With its frequency response of what? GR of F. So output of the receiving filter is given to the equalizer. So I denote the frequency response of the equalizer as GE of F. Okay. So this GE of F means the equalizer output is given to the detector. Okay. So this is the block diagram of a system with equalizer. So in the earlier case, without equalizer, I have discussed it, right? This diagram. So after the receiving filter, it was directly given to the detector, right? There was no equalizer block. So here with equalizer, after the receiving filter, I will be using the equalizer. So the frequency response of this equalizer will be, you see what it will be, okay? Now it can compensate that intersymbol interference. I hope this diagram is clear, no? This is a digital PM transmission only with equalizer. Okay, I said what is the difference between the diagram, what I discussed at the beginning of this module, and what I am discussing today. So the difference is what? Output of the receiving filter was given to the detector directly in that case. Here it is given to the equalizer, then output of the equalizer will be given to the detector. So this equalizer will eliminate the effect of intersymbol interference. Okay, just yeah. So the demodulator, I said, consists of what? Receiving filter with the frequency response of GR of F in cascade with the channel equalizing filter that has a frequency response of what? G of F. That one. Since GR of F is the what? Frequency response of the receiving filter, right? That is matched to the what? Frequency response of the transmitting filter, right? And they are designed so that their product will satisfy that equation 1. What is that equation 1? GT of F will be equal to square root of X RC of F into e power minus J2 pi F T naught, right? It should satisfy that. So G of F will compensate for the channel distortion. Okay. So the equalizer frequency response must equal the inverse of the channel response, I can say. So I can write G of f will be equal to 1 by C of f. So C of f is the what? Frequency response of the channel, right? So the equalizer frequency response should be equal to what? Inverse of the channel response. That's what we say. So which is equal to, I can write it as 1 by C of f into e power minus j theta C of f. So I said the equalizer frequency response will be what? 1 by C of f, right? And its phase characteristics, that is theta E of f will be equal to minus theta C of f. So this is the magnitude response of the channel. So this is the magnitude and is the phase response, right? So the phase response of the equalizer should be equal to minus theta C of f. So what I mean to say is the equalizer, I can say as the what? Inverse channel filter to the channel response, because GE of f is equal to what? 1 by C of f. Okay. So the frequency response of the equalizer will be is equal to what? Inverse of the channel frequency response. Then it will be able to compensate that intersymbol interference. Hence it is known as, I say, equalizer is said to be the inverse channel filter. At least you should be able to catch this point. Equalizer is nothing but a what? Inverse channel filter of the channel response. G of is equal to 1 by C of f. Okay. So, means the inverse channel filter will completely eliminate the intersymbol interference. Means that equalizer, channel equalizer, get caused by the channel, right? So, because it forces the intersymbol interference to be 0 at the sampling times t equal to nt, so we call that as a zero forcing equalizer. Yeah. So we should understand this. Why we call that as a zero forcing equalizer? Why we call that as a zero forcing equalizer? Because what is that? Equalizer, or you can say inverse channel filter, will be eliminating the intersymbol interference completely, which is caused by the channel, because it forces the ISI to be 0 at the sampling time. What is the sampling time? T equal to nt. Hence we call it as a zero forcing equalizer. So now I can write the output of the detect means equalizer, okay, which is nothing but what? Input to the detector, right? Output of the equalizer is nothing but what? Input to the detector will be of this form. So Ym is equal to Am plus Wm. Means Ym is the what? Received symbol at a time instant m, which is equal to Am is the what? Transmitted symbol at a time instant m plus the noise. Yes, I hope this is clear. This is the input to the detector, means this is the output of the equalizer, what I mean to say. And Wm is the what? Noise component, I said. And we all know it has zero mean, right? The noise, white noise has zero mean, and its variance is the formula of this. Variance divided by from minus infinity Sn of f is the frequency response of the receiving filter, then frequency response of the channel equalizer, right? So this and this will be equal to what? Is nothing but XRC of f, right? By C of f square. I'm substituting that value over the limits minus W to W. And this Sn of f is nothing but the power spectral density of the white noise, right? And its value will be equal to N0 by 2 for the known channel, right? If it is additive white Gaussian noise, its possible density is N0 by 2. Okay, if I substitute this value in this equation, I get the variance of the zero forcing equalizer. Okay, the noise variance of the zero forcing equalizer. Get the output of the zero forcing equalizer. So this is what the expression. What I mean to say is the noise variance at the output of the zero forcing equalizer is higher than the noise variance at the output of the optimum receiving filter. For the case where we have considered channel is known, in that case it was how much? It is N0 by 2. It is a variance, right? And this is the expression for what I said, noise variance at the output of the zero forcing equalizer, and its value is more than the value of the variance of the optimum filter. Okay, this is what I wanted to convey today. So, if you have any questions to ask, you can ask from your side. So, I would love to stop from my side for today's class. So now I'm giving you a chance to ask any questions related to all these topics, whatever I have discussed. People are there.
Yes, sir.
Yes, sir.
ಅರ್ಥ ಆಯ್ತೇನೋ ಹೇಳಿದ್ದು If you have any questions, please ask. This is the questionnaire time to discuss. I tried my level best to explain what equalizer is. Still, two more class I need to explain about that adaptive equalizer, then decision feedback equalizer. I will come out with the example. Okay. Even I would like to convey same thing what I have discussed today in a different way, so that that will make you to still understand better. Okay, I have those PPTs. So today I told as per your prescribed textbook content. Okay, so let me convey the same thing. I feel you will be able to understand better still. Okay, so you don't have any questions to ask then. So it is 3 to 4 o'clock already. From morning you are tired listening so many hours of class. Vishnu, don't have questions?
Sir, no questions. I missed some part when you for some network issue. I'll cover it up again, sir.
Okay. I will share also this. I will upload.
Okay, sir.
We all can write your revision in chat box. Huh? I think some have written already. What about others? I think you came to know your IMRs. Yes, your IMRs have been shared.
No, sir.
No, sir.
Okay, not yet shared because we're saying it will be shared. Okay. Oh, not to, I think, your parents. Fine. It's not yet shared, no? Okay.
No.
What, Pranav?
Sir, IMX have not been shared, sir.
Not been shared, huh? Okay. Let me see. Because already they have collected from us, from all the course coordinators, they said it will be shared through mail. So no questions then?
No, sir.
Okay, so please write your revision in this chat box. Let me then close. Yes. Nandish Reddy.
Sir.
ಗೊತ್ತಾಗ್ತದೆ ನಂದೀಶ್ ರೆಡ್ಡಿ ಅರ್ಥ ಆಗತ್ತಾ
ಸರ್ ಅರ್ಥ ಆಗ್ತಿದೆ ಸರ್
ಆಗ್ತಾ ಇದೆ ಹೇಳು ಗೊತ್ತಾಗಿಲ್ಲ ಅಂದ್ರೆ ಸಂಕೋಚ ಪಟ್ಕೋಬೇಡ I don't know to what extent you are able to understand present symbol, previous symbol.
ಓಕೆ ಸರ್
What about Teja? Ritu? Ritu is not there today. Ritu is there. Okay, then return.
Yes, sir.
Ritu is there. No, Kavya. Kavya is left. What about Ashwin? Ashwin,
Yes, sir.
are you understanding, man?
Yes, sir.
Okay. Okay, then we'll see you tomorrow, third hour class.
Yeah.
Example. Yeah. I hope everybody has written your revision in the chat box.
Yes, sir.
Yeah, thank you.